Hi, this is Sudeep Panchanda from Quite Easily Done, and welcome to another videos from Know Your Boards. In the Know Your Components series, we had talked of a component which is called the 555 timer IC, which is an 8-pin IC. When we were studying about this IC, we had said that this 555 timer IC can be used in 3 different modes. The first being the A-stable mode, where the output of the 555 timer would not be stable in 0 or 1, so it does not have any stable state, and so the output would keep flipping from 0 to 1 and then coming back from 1 to 0, and will keep on going on this cycle. The next state we had talked of was a monostable mode, in which we said only one state of the 555 timer would be stable, which is the state 0 or the off state, and when we provide a trigger to it, the 555 timer's output would jump from the 0 state to the 1 state, will remain there for a while because it's an unstable state, and will fall back to its original stable state of 0. So we'll get a good nice pulse as an output. And then the last we talked of was a bistable state, wherein the 0 and 1 state of the 555 timer both will be stable. So when we are at the 0 state and we provide a trigger, the output would jump to 1, will remain at 1 till when we don't provide a reset input to the 555 timer, which would cause it to go back to 0. In this video, we will be talking about the 555 timer in the A-stable mode. We would first look at a quick demonstration of the board which implements the 555 timer in the A-stable mode, and then deep dive into the circuit diagram of the same. So let's get started. Here we are looking at the board which implements the 555 timer in an A-stable mode. If you look at the board, what it is doing right now is the output of the 555 timer is toggling between the 1 and the 0 state, the on and the off state, which can be seen by the blinking of the LED light over here. The frequency at which it blinks, the amount of time that it's going to remain on for and the amount of time that it's going to remain off for, is determined by the capacitance value which is used over here and the 2 resistances that are there on the board. So let's look at the circuit diagram and understand how these resistors and capacitors are being used to create the 555 timer in the A-stable mode. Let's go ahead. Now we are looking at the circuit diagram for 555 timer in an A-stable mode. Again, so we would look at the circuit diagram as an increment to what had we looked at before as in the 555 timer monostable mode. Now if we first understand how the monostable worked, it would be easier for us to understand the A-stable mode. Now we'll break down the entire circuit into components of how it's working, and that would help us understand it better. So like always, we have the pin 3 of the 555 timer as the output, and the output goes to the LED via resistor and also to the output header pin. This is pretty standard across all modes of 555 that we have seen till now. We again have is the pin 5 of the 555 timer grounded with a capacitor for noise filtering. We again have the same pin 1 and pin 8 used for power supplies. Again, like the monostable mode, we have the reset pin on VCC because we would not be doing the reset thing over here. The difference, however, now is earlier we were used to have is a trigger button, which is now replaced by a connection which is over here. So TRG over there actually means that this gets connected over here. So what we had seen before was that the discharge pin, the pin 7 of the 555, was connected with the pin 6, the threshold, and then we had a RC circuit in series. We again have RC circuits over here, but this time the trigger voltage at the which is the pin 2 of the 555 timer, and the threshold, the pin 6 of the 555 timer, would always have the same voltage because they're obviously connected together. The discharge now has an additional resistor R2 over here, and like before we have is a VCC power supply going via a resistor to a capacitor creating a series RC circuit. So in this case, the difference is we have is VCC R3 in series R2 and then the capacitor C2. So this is an RC circuit with two resistors in series. So we will look at things in a minute. So this is the overall components, the understanding of the structure, and like always we would look at the truth tables to understand what happens in different scenarios. Now let's say we just assembled the entire circuit and we've switched on the power. The capacitor C2 would be discharged, would not be having any charge in it, and hence the potential difference around the capacitor C2 would be 0 volts, which would mean that the voltage at pin 6, the threshold, and the pin 2, which is trigger, would be 0 volts. Once that is the case, and we know the output is 0, right? So let's go back to our truth table over here. When our output is 0, our ground is discharge pin 7 is connected to the ground, right? So this is actually connected to ground. Yep. Okay. So what happens now is we look at the voltage at the threshold and the voltage at the trigger. We said is going to be same. This capacitor would start getting charged, would get charged while we are out. VCC, R3, R2, and then capacitor. This is our RC circuit, and we said the amount of time the capacitor C2 would take to charge would depend on the value of capacitance C2, in this case R1 plus R2, because these two are resistance in series. So now the capacitor would start getting charged and a potential would start getting developed around it, which would cause an increase in voltage at the threshold and the trigger. So we are saying when the voltage around this point is less than 1.667 volts, the scenario at that time is the comparator 2, which is the right one over here, is doing a comparison between threshold, which is less than 1.667 volts, and is doing a comparison with 2/3 of VCC. The 2/3 VCC, this is 3.334 volts, being on the inverting terminal, and the non-inverting terminal, the threshold voltage, being less than 1.667 volts. Because the comparator is comparing a voltage which is lower on the non-inverting terminal, the output comes out to be 0, which is the reset for the flip-flop. Then we look at the other comparator. The comparator 1 has a 1/3 VCC as an input to the non-inverting terminal. The inverting terminal has an input coming up from the trigger, the pin 2 of the 555 timer, which we said is less than 1.667 volts. So now the comparator 1 is comparing 1.667 volts on the non-inverting terminal and less than 1.667 volts on the inverting terminal, giving us an output of 1, which is the set of the flip-flop, which causes the output to go 1, right? So at this stage, when the capacitor is charging, we're getting a 1 output. This is still when the voltage across the capacitor is less than 1.667 volts. As soon as the voltage crosses the level of 1.667 volts, which is greater than 1/3 of VCC, and still less than 2/3 of VCC, this is the stage that we get into. At this time, so this capacitor is getting charged, right? And when the charging is now increasing, we come to a stage where the voltage across the capacitor is between 1.667 and 3.334 volts. In that case, now the comparator 1 is now comparing between 1.667 volts and a voltage greater than that on the non-inverting terminal, which causes the output to go to 0. And similarly, the comparator 2, like earlier, is still having an output of 0. And 0 and 0 on the flip-flop causes a no change status, which means it will remain as 1. Now once this capacitor is now getting charged further and the voltage across the capacitor is now greater than 3.334 volts, which are the inputs to the threshold and the trigger, we see a change of status happening here.
The comparator 1 is comparing 1.667 volts on the non-inverting terminal, and on the inverting terminal has a value greater than that, so the output is 0. But now the comparator 1, which is this one over here, is comparing voltage of 3.334 on the inverting terminal and a value greater than that on the non-inverting terminal, which causes a value of output of 1 on the comparator 2, which is here, which is the input and the reset of the flip-flop. So which basically, because of this, now the flip-flop gets reset and the output goes down to 0. When the output goes down to 0, this transistor over here is switched on and the discharge is connected to the ground. So this discharge pin 7 is now connected to ground. So what is going to happen is this capacitor would now get discharged via the route of C2 and R2 and go into the discharge pin to the ground. So the difference here is when the capacitor was being charged, it was getting charged via the route VCC, R3, R2 and capacitor. That was the RC circuit. While discharging, the route is C2, R2 and the discharge pin going to ground. So the amount of time that the output is going to remain as 1 would depend on R2, R3 and the C2 capacitor's value. Whereas the amount of time that it will remain in the off status would depend only on the values of C2 and R2. So I hope this explanation and the tables over here is helpful to understand how the astable mode works in a 555 timer.
Thank you very much for watching the video. We would love to hear your comments and feedbacks. So please write down to us in the comment section below. Let us know of your feedbacks, your questions. We'd really love to have an interaction with you and understand how are you feeling about these projects. Thank you very much.